In this section, we're discussing correlation. This is section 5E in your textbook. To get us started, I want to show you a graph called a scatter plot. This is a useful way to graph bivariate data. What I mean by that is each point here represents an ordered pair. So for this given point, I have an x value, maybe around 100, as well as a y value, maybe around 96. Now, these variables here, along the horizontal axis, we refer to this as the explanatory variable. So this is the independent variable that might be explaining the dependent variable. For y, we often call this the response variable. So this may depend on the explanatory variable. A great explanatory variable, an example would be time. So time might be the independent variable, and the response might be something like sales over time. In this section, we'll be discussing this main idea about correlation. Correlation is a useful way to establish a causal relationship between two variables. To begin, we'll define correlation. A correlation exists between two variables when higher values of one variable, often the x variable, consistently go with higher or lower values of another variable. This is saying that as x increases, y either increases with x, along with x, or it decreases. It will not appear in your textbook, but in case you see this out in the real world online or any research articles that you may be reading, there is a measurement for correlation, and we often use a R value. You may say this uppercase or lowercase. R is like a ratio, and it is bounded between -1 and +1. It can be equal to these values. If it is equal to positive or -1, then it has exact linear correlation. We want to focus on these main descriptions. Positive correlation refers to a relationship between two variables such that they increase together or decrease together. So as x increases, y also increases. Or if the data was not given to you as a graph, it was maybe presented in a table, if you see that x is decreasing and y is decreasing as well, then that also signifies that you have positive correlation. Statisticians will use R to measure a correlation, and if the R value is between 0 and 1, then that suggests that there is positive correlation. Negative correlation refers to the relationship when two variables tend to change in opposite directions. So as x increases, y may decrease. Statisticians often examine the R value, and you may see an R value between -1 and 0 if there exists a negative correlation between two variables. Now, two variables may have no correlation. And no correlation, this would be either very close, so R would be either very close to 0 or exactly 0. This means that there is no apparent relationship between the two variables. If there is a strong relationship, and you were using software that would measure the R value, strong relationships are measured when R is very close to -1 or 1. When this occurs on a scatter plot, you will see that the data is very close to a linear trend. We call that the trend line. So if that R value gets very close to positive or -1, then that suggests you have a strong correlation. Now, if you have a large data set, R could be smaller, and you could still have a strong correlation. So we want to be careful with that. But overall, in this assignment, we're trying to identify when we have positive or negative correlations, or strong or weak correlations. A strong correlation will be when the points are grouped tightly together. A weak correlation will occur when you have more dispersion. We'll now go into a few graphical examples. This is a common set of data. I'm going to talk through a few of these. So for the first graph on the top left, these are tightly fit. You could draw a line straight through all of these. You'll see that the R value for this set of data is actually equal to -1. The line that I would draw through this has negative slope. So that means as x increases, y is decreasing. So for the point here, the x comma y value, so the x value, as it gets bigger, as I go to the next point, the x value would be bigger here, the y value is smaller. So this has negative correlation. This has strongly negative correlation because it's very close to a perfect line. The next graph that I have here is quite tight as well. So in real life, you're not going to see a perfect trend line in most of the cases. This is strongly negatively correlated here. As x increases, y is decreasing. On the top row, the description here, so you'll see the R value is pretty close to 0. These would either be weakly or not correlated. If we wanted to describe it as weak correlation, then these would be weakly positively correlated. You can see that I could try to fit a line here. It does look like maybe a few of these as x increases, y also increases. However, that R value is quite low. For the graph on the second row, these are strongly positively correlated. As x increases, y also increases. For the middle on the second row, these are strongly positively correlated. As x is increasing, y is also increasing. And the last graph that I have here, these are not linearly correlated. We could see that there is a relationship, but in this section, when we talk about correlation, we're referring to linear relationships. And here we do not have such a relationship. So these would have no linear correlation. I'm going to go through a few graphs to describe correlation. Here you'll see that I have a chart, and in the left-hand column, this is listing the number of hours a person exercised per week. And in the right column, we have something that is called the BMI, so the body mass index. And this is somewhat controversial. It is not a perfect measurement, but here each row represents an individual. So we have the hours they exercised as well as their BMI. When we graph this data, we do see an overall trend that suggests that as a person exercises more per week, their BMI tends to decrease. You'll also see in software such as Excel, which was what this graph was made in, we can plot an actual trend line here, and we see that we have a negative correlation. The R value, so Excel will return an R value, we can see that that is negative. So a negative value for R tells you that you have negative slope, a line that has negative slope, those will occur together. And this is telling us that we have a negative correlation, a negative relationship between these two variables. So as the number of hours in exercise per week increases, BMI tends to decrease. When we look at sales of an item compared to price and advertising. So in this scatter plot, we have two different trend lines here. The blue line I'll talk about first. For the blue trend line, the X values represent the price of an item, whereas the Y-axis represents sales. And as we might assume, as the price of an item increases, then we see fewer sales of that item. The R value for the blue data here is negative, and that suggests a strong correlation between price of an item and sales, so a strong negative correlation. As a company spends more in advertising, that's what the orange scatter plot here is representing. As a company spends more in advertising, we see greater sales, so greater value in sales. This data suggests that those two are positively correlated. no correlation, when you have no correlation among variables, you really shouldn't see any trend lines. You shouldn't see any relationships. This is sometimes called a sneeze plot. Kind of looks like we just sneezed on the screen. There's really no rhyme or reason for where these points lie, and I don't see a general trend. This is an example of a graph which has an R value of exactly 0. And if you ever see this word residual, that's a good thing when you're looking at a residual plot. Scatter plots are for bivariate data, but this is an example of how you could indicate a third variable. So here salary was used by using color on the scatter plot. In this scatter plot, we do see a trend here, and we see a positive correlation. So you could draw a line that goes through around this area right here, and we see a positive correlation between the number of home runs a baseball player hits and the bases on balls for that same player. This is seen by the R value in the top left. R is equal to 0.47. So in real life data, you don't always have an R value that is exactly 1 or -1, but this is a reasonably high R value, especially for the amount of data included in this. This was a strong relationship between the two variables. In this chart, there really is little relationship between the on-base percentage and the defensive percentage. So you'll see these scatter plots, there isn't a significant pattern between these. And the correlation value here, so the R value was quite small, 0.07. Now in this chart, this is presenting a little bit differently. So here we're using two trend lines, and we see that we have chicken consumption by Americans in the United States and crude oil imports. And the correlation value, so R is equal to 0.899899, and that's quite a high R value. This chart is intended to get you thinking about whether the possibility of a correlation is necessarily implying a causation. While correlation is a helpful way to identify causation, it does not necessarily imply causation. And so the important thing to remember when you're looking at correlation is that correlation does not imply causation. A correlation alone is not enough evidence to establish causality. When you're using correlation to establish causality, there are a few things to consider. Consider whether the correlation could possibly be a simple coincidence. Consider whether there could be an underlying cause for the correlation. And also consider whether there is truly a direct cause or whether there is a third variable that is possibly causing the relationship between the X variable and the Y value. And I'm going to give you a couple of examples. So keep in mind, we're looking for what are called spurious relationships. In number 2, if there is an underlying cause, we discussed confounding variables before. If we were to graph ice cream sales in Arkansas, as well as crime rate in Arkansas, we might see a relationship between those two variables. They might be highly correlated. However, we would not suggest that the ice cream sales imply a causal relationship with the crime rate. Most likely, there is a third variable, perhaps warm weather, that is a confounding variable that is causing both of those, and that is actually the true reason that they would be correlated. So perhaps during summer months, ice cream sales increase, and also if you've looked at crime rates before, those will increase during warm weather as well. This is an example of a confounding variable. So warm weather is actually causing the X value and causing the Y value, and that is why to increase. So warm weather causes the X value to increase. Warm weather causes the Y value to increase, and that is actually the reason for their correlation. We could also have a relationship due to a mediator. And so here we might see when we graph college students' family income with their ACT scores, there is a positive trend between those. But we must consider that there could be a possible mediator. And so wealth does not imply ACT scores. There could be a mediator that, because those students have wealthier families, they're able to take the ACT more often and therefore increase their ACT scores. Whereas if your family is on limited income, you may not be able to take the test more than once and increase your ACT score. So this is an example of a mediator where that third variable is actually playing a role in this relationship. So the wealth would be an explanatory variable for having more attempts, and then more attempts would be an explanatory variable for having a higher ACT score.